Hi everyone, I hope you enjoyed the brief break. I'll start again now with the final session for today, which is on using the scheduler on ARCHER2, Slurm, to submit jobs and actually run things on the compute nodes. Okay, so here we go. So we're going to take, I think, a little over an hour to get through this, but I hope we should be able to finish before 4 o'clock, certainly, which is the sort of official, if you like, end time of the course on both days. So we mentioned Slurm earlier on when we were looking at the diagram of the layout of ARCHER2. So it's how access to the compute nodes is managed. So it's referred to as a scheduler. So its job is to manage resources. Resources essentially means compute nodes and how they're made available to users. So it's a batch system. So you submit jobs to it, which can either be commands in scripts, sequences of actions to take and things to do, or else to just start an interactive session. It will go into the queue, and the Slurm scheduler will try to work out when the jobs that are in there waiting should be run, which nodes will they go on, how long will they have on those nodes, and it will try to do that in what is created to be a fair way. So we've got some commands here. There are actually a lot of Slurm commands. It's a big piece of software actually, which makes sense. It has a lot to do. Most of those commands we don't really need to worry about too much. Here are some of them that might be useful. And we'll go through them through the course of this page. So I won't bother talking about them just now, but we'll see as we go through this material what they're all about. So some of the Slurm commands are reserved, if you like, for root, for the people who maintain the system in the systems team, but other ones are available for us as users to use. They generally do things like let us query the state of the system, query jobs, query the queue, and of course we have other tools for submitting jobs and controlling jobs. Our own jobs, of course, only not other people's. So we're going to start out with a fairly simple command, sinfo, this one is called. And its purpose is really to show us the state of the system. So if we run it, just in the command line, I've still got my terminal open here, so I'll use that. I'll show you what we find out in a second. If you just run sinfo and press enter, you'll essentially get some output listing all the nodes on the system and what state they're in. So if we just try that now, so I've just typed sinfo with no options or arguments and enter, and you get, well, quite a lot, to be honest. Let me drag it all the way over. What I can do is I'm going to use this also briefly to just talk about the concept of partitions, because I think this can be a little unusual sometimes. So this is listing all of the nodes in the system. The compute nodes on ARCHER2 are referred to by their names, which begin with NID and then a number. So in the same way as here at my prompt, I'm logged into LN04, login node 04. These nodes, so this one here, let's say NID 002128 means this is node ID 002128. So if you wanted to ever talk about a particular node, that's how you would refer to it. And as it goes down, we see nodes listed. So this is a whole list of nodes with different numbers. and then some really huge lists of nodes covering ranges of potentially hundreds or thousands, maybe, of node IDs. And these are listed by their partition, whether they're up or down, their state. So partition, first of all, Slurm uses this term partition to refer to a group of nodes. So, so these are groups which may overlap with one another. So if we start at the bottom actually and work our way up, it's first of all talking about the serial partition. So this is actually just the partition containing the two data analysis nodes. Then there's another partition being mentioned, higher mem. Higher mem contains all of the nodes which have the higher memory. So what was it, 584, I think, nodes which have 512 gigabytes of memory rather than 256, the standard compute nodes. So these lines here, which begin with higher mem, these are, this is telling us the state of all of the nodes in the higher memory partition. Then we finally got the biggest partition, standard. The standard partition of nodes includes all of the 256 gigabyte standard memory nodes, as well as all of the 512 gigabyte memory nodes. So everything in higher mem is also in standard. You can actually see, I think, yes, you can actually see some nodes are listed in both. So you can see NID 002798 is listed as being in the drain state in both partitions. That really just means that how this matters in practice is that when it comes to write a job script, and we'll see that a little bit below, you choose which partition, which type of node you want your job to run on. And then, of course, there are different states. We don't really need to worry about most of this. This is really for the systems people to care about mostly. They can set nodes to come into service, to go into reservations. For example, we have our reservation, which is active at the moment because we'll be running jobs in this session. And we'll be running, well, on some of these nodes, somewhere in one of these reservation groups. Some nodes are idle, they're doing nothing. Others are draining, which means that they're running things at the moment, but they won't be allowed to run things once they're finished because they're possibly being taken into a reservation or being taken out of service for maintenance. What else is there? Mix means that this node is partially allocated but not entirely. Alloc means that the entire node is being used for a job. So this is just a quick way of just seeing what's happening as a whole on the system. It's essentially, yes. So yes, there is a time limit column here, but the way that ARCHER2 is set up, that doesn't matter for the partitions. Yes, and here's just a list of some of the most common fail states that you might see. Fail states, the most common, oops, and there goes my mouse. It'll be back in a second. Some of the most common states that the nodes will be in. Something kind of see that this is some of these node lists are so long that reading this is really difficult. So something that's handy is you can pipe it to less -s, which means put it on a single line, and then we get it in this form, and you can use the right and left arrow keys to scroll through these. A few of these Slurm commands do produce so much output that piping it to less -S like this is actually really handy. And then you can just quit back out of this by pressing Q. If you want to look, instead of at these long lists of nodes, you can instead run sinfo-n-l. I'm definitely going to pass that through to less-s because that will produce a lot of information. So I'll just pipe that to less-s like so. And now I get it like this. And I actually get a little more information for each node now, but I can do this and I can scroll through. I could even, if I want, because I've got it in less, search for a given node here, and then exit again with key. So we do get a lot of information. Something you might spot here is it's listing CPUs as 256, and then on the next column, SCT, sockets, cores, threads, two sockets with 64 cores per socket and 2 threads per core. The reason it's listing 2 threads per core and so 256 CPUs rather than 128, which is the number of physical CPU cores, is that this is allowing for symmetric multi-threading. I can't remember the AMD term for it. Hyper-threading is the Intel name for it, which we almost never use because in terms of HPC applications, it almost always leads to worse performance. Move that just a wee bit back over. There we go. Okay. So we've got a little exercise here. We'll spend 5 or so minutes doing this. Actually, maybe a little less. This isn't such an important one. So we've got here. Let's all start doing this. So we're going to take a look at the resources on the compute nodes. So we can use sinfo-n and then give the name of a node to find the specific information for one node in particular that we care about. And then you can also add the -o option, which means give me this information NCM, mean that we're going to find the name, number of CPUs, and memory of that node. So this is just going to give us this information in particular. But what we're going to do is we're going to try to find all the free nodes in the system. And you can do this, well, there are actually a couple of ways of doing it. You could do it by piping it, maybe to grep or something, but you could also try doing this with just sinfo itself. So I think we'll just spend 3 or 4 minutes, let's say 4 minutes, just doing this, and then we'll move on to actually writing and submitting jobs to the system. So I'll just say let's get back to this at 14:57. We'll come back and see if anyone's found the command to use to list all the free nodes in the system. Again, man sinfo could be very helpful here. You just do man sinfo, and here we go. We can take a look at all of the options and see if anything looks helpful. Okay, we'll come back to that in a few minutes and see what anyone's found. If you do want to ask any questions about doing this while we do it, please go ahead. Okay, so hopefully you've found that few minutes enough to take a look and see what you think the command might be. Has anyone got any suggestions on how to use sinfo to find all of the free nodes in the system? Anything which is currently sitting there idle? sinfo states equals idle. Okay, we've got a couple of suggestions. Great. Okay, so let's see what they both do. So sinfo states equals idle. That seems to have got us everything. I'm wondering why it's showing these nodes as well. It's certainly showing idle and reserve. That seems to have got most of the information, certainly. And sinfo nt idle. Let's see how that works. Sinfo nt idle. Yeah, they're all showing the reservations as well. Lots and lots of nodes. Maybe I should have piped those to less. So the one I believe given, let's see. I think this will also do it. Is this the one also listed here? I believe so. Yes, -- state equals idle. Yeah, I think so. I think that's the case, Julian. So yeah, all of these are ways of doing it. So you can see, given we've sort of, yeah, it's been, I wonder if that's possibly the file system slowdown for that particular node, 002128. It might be, it's been trying to clean things up on the node and finding it tricky because of this weird file system. Although it seems a lot more responsive now. Hopefully it is actually better. Or it could be that it's a job that's gone wrong. It does occasionally happen. But yes, it seems to be listing all these. So we've come up with you, and what we have here is the solution. We've come up with 3 different ways of showing this. So you can see even sinfo, which is just a way of showing the system, is a fairly powerful tool. And of course, we can add extra options to it to find even more out about each of the nodes. We can choose particular nodes to look at, find out lots of details about their hardware and the like with sinfo if we want. But we'll move on to something perhaps a little more exciting now. You can actually start running jobs. So I've mentioned batch scripts. So a batch script is, well, it's something that I mean, this has been in use a long time. I remember learning about this at school, like running batch scripts to do things in, well, DOS that was. A batch script is just a script that just contains commands to do, and this goes through a batch system. So it goes into a queue. Slurm takes the batch script, the script that we write, which contains information on tasks to perform, as well as special information for the scheduler on what resources to use to perform those tasks, places it in a queue, and when it thinks the time is right, it will run it on the resources that it allocates for us. So you may have used Slurm before. I think Slurm is popular enough that a lot of people will have used it, or you may have used things like PBS or SGE, SunGrid Engine, to do essentially the same thing, just with slightly different terminology. But this may be familiar to a lot of you. Really, they come in 2 parts: a header section, which tells us the shell to use and provides options to the submission system, which is sbatch in the case of Slurm. And beneath that, there's a body of the script that contains the commands which actually do the work that we want. And we'll see here everywhere that we have these special options to sbatch. We begin the line with this special #sbatch command, which lets sbatch, when we submit the job, know that this is something it needs to worry about. So what we have here is a fairly simple script that runs a program called xthi. I used to say this xthi and been told that it's actually xthi because xt was a previous series of Cray supercomputers, and hi is in the sense of hello world. So this is essentially a hello world program, if you like, with some useful information. It actually produces some quite useful information to run on a cluster like this. So we're going to run the XT-hire program, in this case, across 2 nodes. So this script, it has well, quite a lot of options. Let's take a look first of all at all of the things that we're passing to SBatch, all of the SBatch options. So we tell it about the job name. So when we want to look up the status of our job or jobs in the queue, we can choose to identify them with names that we give them. We can choose the number of nodes that we want to use. In this case, we're using 2 nodes, so that's 2 nodes of 128 cores, so we're using a total of 256 cores. We're then going to choose how many tasks per node, so that's MPI ranks is the usual case here. So almost always this means we want 128 MPI tasks on each node. So 256 again in total for the 2 nodes. And then how many cores do we want to allocate per parallel process? What we're doing here is a pure MPI run. So we're just saying 1 MPI rank per core and 1 core per MPI rank. So yes. So this is just placing one MPI rank on each subsequent core on each of the 2 nodes. Then we're setting a maximum wall time for the job, 10 minutes in this case, so that's hours, minutes, seconds. The term wall time, if any of you are new to cluster computing or parallel computing in this way, wall time refers to, in this case, literally the amount of time that passes on a clock on the wall, rather than, say, simulation time. If you're running something, you know, maybe that integrates the system through some number of nanoseconds or maybe millions of years, depending on which scale your work is on. This just means that in terms of real time, as we observe it, this can run for a maximum of 10 minutes. Then we get onto the partition. The partition, we're choosing to be standard here. So remember, I spoke a little bit about 15 minutes ago on partitions. That means we want it to run on the standard set of compute nodes, which includes both the regular memory nodes and the high memory nodes. So if the system wants, it's out of our hands, it can run it on the high memory nodes as well. Then we choose what's called a quality of service. We'll talk a little about that in a bit. The quality of service is sort of like a queue, but not really. It essentially chooses which limits are being applied to our job. Depending on the quality of service you choose, you might be limited to running, say, lots of jobs which can't last for very long, or only a couple of jobs which can run for a very long time. It's a way of, it's part of the way that the system is set up to try and keep things fair between users. Almost all the time, the standard quality of service will be what people will use, which just means that you're limited to a certain number of jobs that can run on a certain number of nodes for at most 24 hours. Then we have some another very important thing. We choose the account. This means, in this sense, this doesn't mean, and I think this is slightly unfortunate. It makes people think, I think, of user accounts, but what it's talking about here is actually more like a bank account, if you like. This is saying which budget do you want your job to be charged to. If every job that runs costs some amount of resources, depending on systems you've used in the past, you may have been charged in, say, core hours is a sort of universal concept. how many cores did you run on, for how long, multiply them together, and you get a number of core hours. On ARCHER2, we charge instead in node hours. So when your standard QoS job finishes, it will calculate how many node hours were used to run it, and it will then subtract that cost from the budget that you specify with this line. So in this case, I'm choosing that this job, when it finishes, is going to be charged against the budget which we have for the TA062 course project. Then we've just got a couple more commands. These are a little different. These choose how to place the work onto the physical cores on the nodes. Hint: no multi-thread means that the work is going to be distributed amongst physical cores only. It isn't going to try to use the multi-threading. So we aren't going to end up with say 256 tasks running on 128 cores. It's going to make sure that each physical core gets only one task. And distribution block says how the tasks are going to be assigned to the cores. Block means it's just going to place them 0, 1, 2, 3, 4, and so on sequentially across all of the cores available, which is not the default. The default is to do it round robin style, which is a little weird. I think if you do that, it'll end up placing task 0 on the first socket, on socket 0 of node 0, then the next one on socket 1 of node 0, then task 2 on socket 0 of node 1, and task 3 on socket 1 of node 1, and then go back to the beginning. It's a round robin style, which turns out to not be so good for typical communication patterns. Doing block is most cases the best way to do it. There are ways of changing this as well. You can give options to mpitch to change that. We'll maybe talk about that tomorrow if there's time. So that's everything that's here. Then there are a few other commands. Module load xt-high is just needed to make the xt-high software available. It's been installed. If we do module, if I run here, module avail xt-high, we'll see whenever it gets around to it that there is an xt-high 1.2 installed, so this will load that and make the software available to run. Then we set export OMP num threads equals to 1. You should always do this. So this is an OpenMP environment variable that says we're basically not going to use OpenMP. We're just going to run with a single thread on everything rather than use threads. And even if you're running in pure MPI, you should still set this export OMP num threads 1, because some of the in particular Cray libsize software does have threading enabled, and if that isn't set to 1, you might end up unintentionally running with something using threading that you weren't intending to happen. So if you're running even in pure MPI, it's worth setting this variable to 1 just to make sure that nothing in the background actually accidentally tries to use threading in any way. So when we get around to actually running jobs like this, I'll actually show you this. So we can use sbatch QoS equals reservation, so rather than the standard QoS, and we can then provide an extra option to sbatch, the reservation option, and we give a reservation name. And that means then that we'll be able to run on our reservation. So we do have a reservation for this afternoon. And I've put the details in the Etherpad. So if any of you want to check the Etherpad, you'll find it all there. But I'll also just paste it into the chat now. But if you want to try running things now, our reservation for this afternoon is this slightly messy name that I've just put in the chat, TA062Q, a number underscore 1. So so I'll just quickly show you. Now. Let's go to my work directory. There are various ways of getting to your work directory. I'm just typing it out in full here, but some of you may want to do things like, for example, create an alias in your .bashrc to move you quickly there. So if I move to my work directory, there's my hello. I'll just create a new directory and let's just call it, I don't know, run xt-high. I'm not feeling very imaginative at the moment. And then I'll cd into that. Okay, and I'm just going to create a job script. So the job scripts, when you create them, they don't actually need to have any particular file extension. You can just call them .sh, or you can give them no extension at all. I personally like to give them .slurm extensions, just so that then when I do an ls in the directory and I see that there's some file called something .slurm, I can go, aha, that's a slurm job script. That's just a personal preference of mine. Okay, and then I'm just going to copy this in, because it will take me a while to, oops, I've not actually copied that, have I? It'll take me a while to copy it and I'll make typos. I will change the name, I'll just show you this. I will change the name, I'll just call it xt-high run 1, say, just an example. But otherwise I'm keeping everything here default. So this is just going to run a 2-node job of xt-high. Oh, I didn't mention, which is actually launched via this option. So when you, I missed the most important thing. The final line here, srun xt-high. This is how we actually launch the parallel task. So if you run xt-high by itself, that's just a serial launch. srun is a bit like using MPI run or MPI exec. That performs a parallel launch. In MPI, it makes sure that all of the MPI tasks launched are in the same MPI world communicator, so they can see each other and talk to one another. We don't need to give it any options by default, telling it the number of tasks or the like, because this is part of Slurm, and it is aware of all the options up here. So when we do srun xt-high, we know, or rather it knows, that it's got so many tasks to launch on so many nodes, and that the tasks should be placed on the cores in such a way. So srun is aware of everything that we've written up here, and it knows how to deal with it. So if I just do that, that would just be a normal job launch. I'll just make a copy of it, and I'll call it submit xt-high reservation, because if I wanted to run this, whoops, and that's not how you do it. Because if I want to do it and run on our reservation of nodes for this afternoon, I just need to make a couple of changes. I need to make the QoS reservation instead of standard. And then I need to add another option, which is to tell it which reservation to use. And that's the reservation that I just put in the chat. So I'll just copy that again and add it here. And then if I save that, that's now will let me run that job on that reservation. How do we actually do that? How do we put them in the queue? Well, we just use the sbatch command. So of my 2 jobs here, let's use sbatch and submit xt-high slurm. Submitted, and I can also do xt-high reservation slurm And as long as I haven't made any mistakes, it seems not, that's also gone off to the queue. I'll just very quickly, we do have a little exercise here. I'm actually going to just quickly go on to this and then go back to that. So now if I want to know the status of the jobs, well, there's this SQ command. And if you run that, it's going to tell you about every single job currently in the queue. Some of them will be running, some of them will be pending, some of them may be completing at the moment. At the moment, I'm just scrolling through all of these, and there are a lot of them. So I'm actually going to run that again. Oops, accepted. Now it's a little slow. Okay, let's pipe that to less again. And I'll do a -s once more. So here's every job currently in the system with lots of columns. It's telling us the job IDs. So every instance of a job that's been submitted. So every time you do sbatch something, as you saw, you get a job ID. So here in this example, submitted batch job 23996. It's been a while since then, so job IDs have gone up to the millions now. So we've got job ID 1449567. Then get told which partition it's running on. So you can see there are lots here in the higher mem serial standard. Then the job names, the user who submitted them. This column here, status, you'll generally see one of these three. Pending, PD, means it's waiting in the queue to run. R means it's running at the moment. CG means completing, because there are some cleanup tasks and files to delete, MPI tasks to shut down, and nodes to release. This is done at the end of the job. So generally, jobs spend about 10 or 20 seconds in the CG state if nothing's gone wrong. Then how long has the job been running? If it's running at the moment, the number of nodes it has. And then finally, if the job's running at the moment, you get a node list. So just which nodes have been allocated and are being used for the job. If it isn't running, then you'll get a reason for why it's running. So generally, so I don't know, you can get lots and lots of reasons for why a job isn't running. The two most important ones are priority, which means that it doesn't have a high enough priority yet to run. Every job gets a priority calculated for it, and only the top 100 priority jobs are actually scheduled to be run. Otherwise, they slowly gain priority. So jobs accumulate priority over time until they rise to the top of the list. Resources means that the job has a high enough priority to run, but the resources that are going to be used for it aren't yet available. The way this works is actually fairly complicated. Slurm uses something called a backfill algorithm to work out when jobs are actually going to run. It schedules the big jobs, so in terms of number of nodes first, and then iterates through it, trying to slot in smaller and smaller jobs in the gaps between the big jobs. There are some other reasons we can see here. This one has begin time, which means that when the job was submitted, it was asked to start at a particular time, and that hasn't come yet. QoS max memory per user, I don't think I've seen that before, but that means that the user actually asked for more memory than can be allocated. Some here, so you can go quite a lot into the types of into the job options. So you can actually specify jobs to only start after other jobs have finished. That's what's happened here. This job is waiting for another job to finish before it starts. And then QoS max jobs per user limit means that this person has submitted so many jobs that they've hit the limit of the number that they're allowed to have running at the moment, and these ones are going to wait until some of their other jobs finish. So this is part of the whole, idea of keeping things fair. One person isn't allowed to have too many jobs running at once. Okay, so now we're going to go back a little, and we've got an exercise here. So if you take the job script just above, just copy it into your work directories. Remember, everything for a job has to go in the work directories because when it's running on the compute nodes, the home file system isn't mounted. The work file system is, so everything has to be in the work directories. You can then modify it. You can take information out is the important thing. You can see what happens if you delete the nodes line. Say, take this information out and then try to find the defaults for the SBatch options. So, for example, if you remove the partition and QoS options, if I were to do oh, and I'll just mention this in a second. If I were to modify my regular script here, if I were to delete the partition from it, what's the default partition? That's what we're just going to spend. How shall we spend on this? We could maybe go until past on this, so 6 minutes. Trying to find defaults. I would try to do the first 4, certainly. The 5th one here, finding out the default wall time, is actually a little trickier, and you need to use a different command called sact, so saccount this means, to do this. If you have time, try that out, and otherwise I'll show you. But we'll spend 6 minutes, we'll go until past, trying to find out the default partition, default QoS, default budget or account that it charges to, default tasks per node, and the default number of nodes. The way that you'll actually see this is when you run the jobs, once you've run SBatch on your job to start it running, you'll find output from your jobs. You'll find these files in your working directory, slurm dash, and then this is the job ID. And you can do more or less or just cat, whatever you find easiest. Let's just do cat on this. And if you do this, you'll see all of the output from xt high. Oops, I've scrolled a bit too far. So when I ran xt high there, that was again just the default over 2 nodes. It's told me which nodes I used, how many tasks, where those tasks were placed. You can see the rank 0 task was placed on node 0, thread 0, affinity 0. So this is just placing these one after another. So all of you should now be able to copy that job script. As I said, you can just copy this. If you want to run on the reservation, then just make the changes that I made here, and I'll just pop that up so you can see. You just need to make these 2 changes to it to run on our reservation. I'd recommend doing that just because it means that your jobs should run basically instantly. These jobs are set aside. Nothing is running on them other than any jobs that we as a group in TA062 send to them. Okay, so I'll just let you take a few minutes then to run these jobs. You can confirm that it worked. Fantastic. Yeah, they're very specially set aside. Only people in TA062 can use them. Can I please paste the link in the chat for the slides? Sure. Let me just grab them. The web page. Sure. That one will take you through to the that link will take you through to this material if you want to copy and paste that job script. After some period of time, you know, writing these job scripts becomes second nature. You just remember all of the fields to do for the S batch at the top. You'll just go, yep, I need the nodes, n tasks per node, partition, QoS. You'll remember it. But at the beginning, if you've not written these before, remembering all these pieces of information that you need to provide can be a bit of a headache. Okay, I'll let you carry on for a couple of more minutes. Then we'll come back to this and see if anyone's found out any of these defaults. Hi again, everyone. I hope you've had a chance maybe to run those jobs. Are you okay to carry on now, or would you like a few minutes more? You can just type in the chat if you like, if you'd like a little longer to work on this before we carry on. Julian's also mentioned a really good point there. Julian said that XT-Hire is a super useful program for testing out how tasks are placed on ARCHER2 nodes. This can be very helpful if you're wanting to run multiple subjobs on a single ARCHER2 node. So yeah, so what Julian said is really correct. If you want, you can go down a rabbit hole of creating interesting ways, I'll put it, of setting up subjobs and tasks across one or more nodes. And sometimes you will maybe find yourself wondering if this setup you've created is actually working. What you can do in that case is you can run XT-Hire rather than whatever your application actually is, and it will just print out, as we've seen here, where the nodes, where the tasks are on the nodes, which is really helpful for just checking if you're doing what you think you're doing. Okay, so I haven't heard back from anyone saying that they'd like more time on this. So let's take a look at the options here. As I say, answers here. So I say the first four should have been fairly simple to find by just essentially deleting parts of your script. The fifth one, to find the wall time, is actually a little trickier. So what you should have found is that if you didn't provide any partition or QoS, your job basically would have been rejected by SBAT. It would have said, well, you need to choose it. I'm not going to run it otherwise. Let's just quickly see the message that we get. So if I try to do this without specifying a partition, so if I try to SBatch that, submit xthire.slurm, it's just going to tell me off, essentially. Please specify a partition name, unspecified error, although it's actually just told me I haven't given it a partition name. And the same would happen if I hadn't given it the QoS. The budget or account that the job is charged to, this can change depending on how your account is set up. Your user account, I mean, here is set up. Most of the time, I believe everyone here should have this set up so that the TA062 account is their default. Let me just add the partition back in and then delete that. And I should have found that this is the case. Did everyone find that? Were people able to test this? Test the budgets and find that it just submits without any issues? I'll try this now and we'll see what happens. Oops, submit xthire.slurm. Yeah, so hopefully you were able to find that. What about 3 and 4? What did you all find out then? As you can see in the solution here, you would have had to maybe change the script a little. Yeah, I'm not sure why I was actually deleting it. So I normally add in extra hashes at the front, but for some reason I was just deleting the whole line. Okay, so was there anyone able to find the default number of tasks per node or numbers of nodes? I won't actually go through running this because we've actually gone past 3:30 now. So if you try to run without specifying that, and then get the number of nodes and use the output from xt high, what you'll actually find is that the defaults are 1 for both of them. So if you don't choose, it will just allocate one node for your run, and it will only create one task on that node. Doing the final one as a setup above, this is tricky, and you need to use this new command saccount. What can happen is if you don't specify the wall time, so I'm actually going to do Julian's suggestion here. So if you put in a space there, that essentially deactivates our time specification. So now we aren't saying at all what we want our wall time limit to be. And I'm going to submit that job. We can then use this command here, saccount, and this gives a whole load of information about jobs which are running, but we can choose with this O option to specifically get some field of information about it. So it actually gives us a little warning here about it. But if I am quick enough to grab it while it's running, I can now do saccount and then J, and then give it the job number. Oh, actually, no, I think this actually works with historical jobs as well, actually, I think. And we find that the default time limit it received was 1 hour. This is actually a really useful command, sact. So you can, if you do this, you can go down to this point here. This is all of the information that you can get with it. So you can do -O, and rather than time limits, you could do any of these, and you can give a list of them separated by commas to find out any information you might want about them. Actually, that would also really work. That would also S control would also do it. S control, the job. Actually, no, the job doesn't have to be running either. And you can also add the S control show job, and then you can give it -D. Add some extra information about it. So so you can do just show job, and that will show you a good amount. If you add a -D, it adds extra details to it. Quite a lot of extra details, I think, actually. So but yeah, S control is another option. S control can actually also help you with other things. So if you want to find out the name of the reservation, so you can do, well, you can do res or you can do reservation. This is also a way, if you've forgotten it, of finding out the name of our reservations. So you can see every reservation on the system with S control. So yeah, as you say, there are other ways of doing it. Slurm has a lot of tools, and you can often use different tools to get the same information. Okay, so some of these things you cannot provide and get useful defaults. I'd say a 1 hour default time limit isn't necessarily going to be the death of a job. Running with one node and one task per node is probably not ideal. So these are things which you do want to remember to set. Whoops. And as we saw, you can't get by without choosing the partition and QoS. If you don't know if you don't set those, then well, you can't really rely on Slurm to choose what's suitable, what suitable partition and QoS you want to use. As for checking on the state of jobs, well, we saw SQ. It tells us every job on the system. You can pick out a particular user. So let's just pick some person, BZ1. You can just check their jobs in particular. You can also use this to check your own jobs. If you do SU and U and then like this, I would see my own jobs. I don't have any at the moment. Or you can also do SQ me to see your own jobs. So if you were submitting a lot of jobs to the standard QoS, so not going to our reservation, you might see them queuing up there until resources are released for them to use. If you do run on our reservation, they're probably going to run straight away, so you may not even be able to catch them with SQ if you aren't fast enough. If you start running a job and then realize you've done something wrong or just don't think it's necessary anymore, you can cancel it with scancel. You just run scancel followed by the job ID that you get. And of course, if you didn't get it when you sbatched it, you can grab it later on with SQ. And we did note how srun is important. So in our submit xthi, I'm still calling it xthi after mentioning how it's actually xthi. In our xthi job script, here I am just on our standard QoS job script. Our srun command here, this is what performs the parallel launch. But generally, this section here is going to do several things. It's going to make sure that we load any modules that we need to load for our job to run. Here's the thing I mentioned about how OMP num threads should always be set, even when you aren't using OpenMP. So if you're just doing pure MPI, always make sure it's set to 1. And then there'll be at least an srun command. So what I'll quickly do actually is we'll quickly take a jump over to the documentation. So I've just got to randomly open the page for running Nectar++ jobs on ARCHER2. So you can see here we've got much the same thing. Hopefully that's actually, let me zoom in a little bit on this, make sure it's big enough for you on the screen share. So if you were running a Nectar++ job, you would have the same information at the top of your script. You choose a job name, how many nodes, how many tasks per node, and so on. Set the partition QoS. Then here we go. We load the Nectar++ module. Set OMP num threads. Then there's some extra stuff to do. In fact, this is a little different on the srun command. So there's some extra variables that need to be set here to run it. The distribution, it seems, for Nectar++, the best way to do it is block cyclic. So that's set hint multi-thread. You can see these are being set here as options to srun rather than sbatch options. If you put them up here under sbatch, it just means that they will automatically apply to any sruns in the script, and then it just performs the run. Or we could look at, say, VASP. Let's look at a VASP job script. Here we go. And you'll see it's much the same again. What we do is we just start up bin bash. There's our shebang to say it's to run using bash. All of our sbatch options. We load a module. We set OMP num threads, and we srun. In this case, we call VASP standard. And again, we have these options: distribution, block, and hint no multi-thread, which we, in our job script, chose to just put as options to sbatch. But they always take the same form of, oops, I've scrolled down a little bit somehow, of setting up our SBatch options, followed by loading module software, and then running our parallel application. So very simply, srun xt-high does everything here. It creates all of our MPI tasks. It pins them to the correct processes, to the correct processor cores on each of the two nodes, and then it runs them. Something which you may want to do on ARCHER2 is to underpopulate, which means running with more memory or more memory bandwidth on each task by not using the full number of cores on the node. So here's another little exercise, and we'll spend, say, I'm not sure we need to spend much time on. Let's spend five minutes on this. We'll come back to this at 10 to 4, and then we'll get through the rest in about 10 minutes or so because it's not too detailed. So using a script like this again, either this one or the one to use the reservation, we want to see, can we run on 4 tasks using only 64 tasks per node, on 8 nodes with 2 tasks per node only, but 1 per socket, or on 4 nodes with 32 tasks per node, making sure that each of those tasks are spread evenly across the 8 NUMA regions on the node. So let's spend five minutes just modifying your job scripts. You should just be able to change the options up here, then submitting them to the queue, and taking a look at the output in these slurm-jobid.out files, seeing the output that xt-high gives you and seeing if it makes sense. And we'll come back to that just after 10:02. Hi again, everyone. Hopefully you've had a chance to try out those jobs. This should make sense, and running the jobs themselves should be very fast. So, so who knows what options we should do to achieve number 1, running on 4 tasks with only 64 tasks per node. These are just the options that you would give to the SBatch directives at the top of the script. So let's open one of them. Submit xt-high.slurm. So if we were going to run on 4 tasks only, 4 nodes only, with 64 tasks per node, we would just change it like this. And that's fairly simple. As we go into tasks 2 and 3, things become a little bit more prescriptive. So if we were going to run on 8 nodes, 2 tasks per node and 1 per socket, any ideas there? I suspect possibly you're looking at this and thinking it's maybe a little bit obvious. So if we were wanting to do that, so remember the socket just refers to really which of the 2 physical CPU chips on the node we're talking about. So if we were wanting to do this, then we would first of all say, well, okay, let's just take 8 nodes. Let's just ask for 2 tasks per node, sure. And well, we wouldn't really do CPUs per task here, so we would, well, I'll just disable that line. And instead, we would create a new option. Oops, I won't create it on that line though. I'll create it here, which would just be sbatch. And this would say n tasks, n tasks per socket. So the vocabulary used, thankfully, is matches well to natural language. We would just say we just want 8 nodes, 2 tasks per node, and 1 task per socket. It maps directly onto the Slurm directives. And finally, the next one's a little bit more prescriptive again. So let's just start off. We say, first of all, we want 4 nodes. Well, okay, let's ask for 4 nodes. Then we want 32 tasks per node. Fine. N tasks per node is 32. Then it's saying this next thing is we want an even distribution across the 8 NUMA regions on the node. So this is important now. So so if we have 32 tasks, we want them to be spread across the whole 128 cores, if you like, to make sure that we're keeping the same number across each of the 8 NUMA regions. We now want to use CPUs per task again, but in a slightly different way. We want to essentially pad them. So let's bring that back in. Let's make it, first of all, 16 tasks per socket. That's the first way that we're going to make sure that they go across both of the CPUs. And then we're going to use CPUs per task. We're going to set that to 4. This means that we're going to have 1 task on 1 core, then 3 tasks, then three cores doing nothing, then another task, and then another 3 cores doing nothing. So this is the way that we would pad them essentially across the NUMA regions. Make sure that we don't bunch them all up on one little group on the first 32 cores, where they'd all be using the same NUMA region, and then having to spend a long time talking to the other NUMA regions. This spreads them out, makes sure that they each have their own sort of patch of close by memory. And well, there's the solution, of course, there. Okay, so I'll try to wrap this up quickly now because we're almost at 4 o'clock. Some of you may be just running pure MPI. Other people will be running with hybrid MPI and OpenMP, where OpenMP is giving you threads. This is where this is the sort of more traditional, I guess, route for using the CPUs per task directive, where we leave gaps between the MPI tasks where there are cores available to run the OpenMP threads. So the way to do this, well, I'll just actually follow what's here in the material rather than write it out, is that in this case, we'll be asking for 2 nodes. We'll be asking for 8 tasks per node. So only 8 MPI tasks this is, but then each of those would be using 16 threads. And we do this by setting CPUs per task to 16. So we'd be placing the tasks 16 CPUs apart from one another. And then we'd be specifying threads per core is equal to 1, as well as export OMP num threads equals 16. And these all combine together to make sure that across those 16 CPUs set aside for each task, we run 1 OpenMP thread on each core. And if you then run that through xxt-high, ss-run to launch it, you'll see that the information xt-high produces shows that this is happening correctly. I mentioned this earlier on during the ARCHER2 section on what makes up the system when we were talking about the NUMA regions first. But with our 4 NUMA regions per socket and our 64 cores per socket, that means that there are 16 cores in each NUMA region. So you don't really want your OpenMP threads to be spanning multiple NUMA regions at all. That means that they're going to be taking longer to use the more distant memory. So this really does limit you, as I said, to up to 16 OpenMP threads per task. There isn't anything physically stopping you from using more, but you'll see performance take a tumble if you do that. So the obvious ways to do this, if you do run hybrid MPI OpenMP jobs, is to run with things like 8 MPI tasks per node and 16 OpenMP threads per task, which means that you'd have 1 MPI task per NUMA region, and then you take it through to 8 MPI tasks per NUMA region, which would instead have you run 64 MPI tasks per node and 2 OpenMP threads per task. Of course, the next step down would be 128 tasks per node and no threading at all. But this really is the limit, this top line here, where you're running with 8 tasks per node and 16 threads per task. Any more than that, and you will see performance drop because of the spreading of threads across different NUMA regions. We've seen that output is written to, and I'll quickly quit here. Settings are, no, okay. Here you can see my output. I'm sure you've been seeing the same slurm-jobid.out files. These contain the merged standard out and standard error streams from your job, from your application. Often, as this says here, if you get in touch with the service desk, this will be the first thing you'll be asked to provide, as well as possibly your job script to help diagnose what's going on. Something you can do is you can redirect it through sbatch directives. You can give --output file name, --error file name options to sbatch to do that, or you can even just redirect the srun application outputs. You would just do you could even just do this if you wanted to send standard out to standardout.txt. So you might do something like that. And what else is that? So this is really just so those are the basics of running jobs. Really, your jobs can be as complex as you need them to be. You can have complex setup sections before your srun, where maybe you pre-process data and move it into place. You can have something run after your srun section. You can customize it as much as you need. What we've got here is really actually quite basic. I would suggest, if you do want to do more, taking a look at the ARCHER2 documentation website again. There's lots more information there on running jobs in various ways, details on the various partitions and QoSs on the system. I'm just noting here, so there are just a few sections here at the end of this page of things that I think are possibly particularly handy for people doing development work. The first two are both the same, different ways of running interactive jobs. So what we've been doing here is we've been running we've been running jobs as batch scripts. We've written a script that says get some number of nodes and then run xt high on them in an automated way without any input from us. We just send it off into the queue and it runs when it gets to the top of the queue. But we can also run interactive jobs. We can reserve a node or multiple nodes for us to use interactively. There are two ways of doing it. One uses salloc, which is just as it sounds, slurm allocate. And so if I maybe just copy this quickly, I can show you this running. So if I just copy that, you run the salloc command, followed by all the same options that you would normally use in an SBatch job script. So the partition, the QoS, how many nodes you want, tasks per node, CPUs per task, distribution, everything is in there, as well as your account. And then after a little while, you'll be told, first of all, that the job is pending. Then you'll get messages saying, waiting for resource. And then finally, you'll be told that the nodes are ready for the job. Your prompt won't change in any way, but now you can get going. What's something else you can actually do just quickly to see if you can SQ yourself, and I'll see my job is running. And I can now do module load S1. So what am I doing? Module load S1. That makes no sense at all. Module load xt high. And then I can S1 xt high, and it will run on those jobs that I've reserved through salloc. Except it is still taking a little time, isn't it? Okay, yep, and then just S1 xt high, and it will again, S1 knows about those options that we chose from the salloc. It knows that we chose 2 nodes, 128 tasks per node with 1 CPU per task. So if I run that, that will start, and we'll then see the outputs coming directly into the terminal. Like so. When you're done, exit will relinquish the allocation, give the jobs back to the queue, and stop the job. And you see the job's over. The other way of running interactive jobs is to go directly onto the nodes themselves. So previously, when I was running the interactive job through salloc, I was still logged into LN04, login node 04. If I use srun like this instead, I can instead go straight onto the lead node of the job. So this will take me onto the node which is going to run task 0, which will run MPI task 0. I have no name, it tells me. Well, no, it hasn't. So then you can just do again module load. Actually, I think I possibly don't need to do this. Module list tells me. I think I possibly needed a login on the end of that. You can module load xt high. I think the configuration here has changed since last time, so I think I do need to check this. And once that's started, we can then srun again. This time, you do actually have to provide some extra options to srun. In particular, you need to give it this over subscribe option, because we've kind of already taken the nodes through the first srun. This is sort of a little sort of recursive slurm, I guess. If we run this, this should then allow xt high to run just the same as before. So this is maybe easier if you want to run again with different options to srun, or else see what the environment actually on the login, on the compute node is like. And you'll see as well, this is doing something very unusual because it's now placing, I think that's because that was run with only ntasks 256. You'd need to then give that the extra options to tell it to use both nodes rather than trying to use the multi-threading. But the important thing is this, you'll see that NID there. So this tells me that I'm actually on the node at the moment. And there are details about doing this on the documentation website. So for that, you would just head here, running jobs, and I think somewhere down here. Yeah, so you can see here example commands as well, and details on how to do this. I think this is just nice sometimes if you're changing code quickly and you want to run it again and again. This can maybe help sometimes if you want to if you just want to reserve a node or two just to run your code on repeatedly. This can help when you're developing. Another way of doing it is to use the short QoS rather than standard. So the short QoS jobs are limited to using fewer nodes. You can only use 32 nodes for a job rather than 1024, and you can only run for 20 minutes at most rather than 24 hours. So it's just a few changes to your script. You just change the QoS like so to short. Make sure your wall time limit is no more than 20 minutes and run the job. So if you do have lots of small test jobs to run, you can go ahead and just send them onto the short QoS to see if your latest work actually will run on the compute nodes. As I said, there's a lot here you can do. These scripts can change a lot depending on your needs. You might need to use different types of nodes for different lengths of time. You might want to run arrays of jobs or chain them with dependencies. We saw one of those waiting in the queue. And Julian mentioned things like running subjobs using fractions of a node. So maybe you want to run a bunch of jobs on one node, each using 32 cores. You can do things like that. There's a lot of ways of doing different things, more than we can cover here, but you can head to the documentation here and take a look at how to do all of that. Okay, sorry, that did overrun a little. We're 10 minutes past 4 o'clock. I hope that hasn't been an issue for any of you, but I hope you found that useful. Before we end things, does anyone have any questions at the moment about any of this? That's been a bit of a whirlwind tour, I know, so I hope it's made sense, but if you have any questions, here's a chance to ask them. Alternatively, as I say, if any questions come to you overnight, you're still more than welcome to ask them tomorrow. Okay, I've got a question. Is XT-High something exclusive for Cray, or can it be installed on any other system? I don't believe it is. I believe that the source code is on GitHub somewhere. Let me take a quick look. I'm almost certain it is. I think it's possibly actually on. I can't remember. Oh, I think I've possibly found it. Okay, I think I've got one I can send to you. Ah, yes, I think a few people have it. It is originally written by, I believe, by people working at Clay when it was still Clay, but I think it's been forked, as Aaron says, by a good few people now. I think I have another link as well.
I think Kevin built one at some point. I'm trying to find.
I think the one I linked is the one Kevin did. I think. I've just found another link through HPE. Okay, and here's a link not to a repository. Yeah, you're right. In theory, everyone ends up writing one. Yeah, there are lots of very similar ones. The link there to HP has just has some more source code of just their own version, I guess, of XT high. Yeah, it's certainly very useful. As Julian pointed out earlier, it's really handy when you're trying to set all these options to Slurm to tell it how to place tasks and threads on however many nodes. If you aren't certain that you've got it right, just quickly, putting in a 5 minute, because it's not even going to take that long, is it? 5 minute long job to run XXT high with that configuration will tell you if you've got it right or not. Okay, anyone else have any questions just now? Yeah, so there are options you can set. There are options you can set to cray pitch, and I can't remember what they are. Some environment variables, which will give you some verbose output. I'll have to look those up. The HPE people know this. There are an awful lot of environment variables to cray pitch, which change the situation sometimes quite drastically. Okay, I can't see any other questions just for now, so I think we can say we'll end there for today. Apologies, we've overrun by 15 minutes from the time we said, which was 10 o'clock to 4 o'clock. I'll stop the recording there.